this is e, so e to the I 3 pi over 2 is cosine 3 pi over 2 plus I sine 3 pi over 2. Cosine 3 pi over 2 is 0. Sine 3 pi over 2 is negative 1. This is negative pi. Okay, so this came out right. We added these together. And I'm bored again already. So I want to do something a little more interesting. These problems are pretty much just, you're going to be able to do these if you recognize what the symbols are and things like that. I want to think about some other things though. Remember, so we know that e to the I pi plus 1 is equal to 0, right? Because this is the same as cosine pi plus I sine pi plus 1. I sine pi is 0, cosine pi is negative 1. This is 0. What about some other interesting kind of numbers? So we know that I is equal to e to the I pi over 2, right? Because this, by definition, r here is 1 times this. This is going to be cosine pi over 2 plus I sine pi over 2. This is 0, this is 1 sine pi over 2, so this is I. Doesn't that mean that I to the 1/2 is equal to e to the I pi over 2 to the 1/2? Well, we know that am to the n is a to the m times n. That means that I to the 1/2 is equal to this times inside here. This is going to be ei to the pi over 4. This is going to be cosine pi over 4 plus I sine pi over 4. I hope that everybody knows that this is the same as 1 over the square root of 2 plus I times 1 over the square root of 2, which is I square root of 2. That's pretty interesting. The square root of I is equal to this. That's just pretty strangely interesting. Something else that I wanted to talk about before we end this series of lectures, and we'll pick up close to this, but as I said before, so you know that, we know that, well, I is equal to e to the I plus, or pi over 2. But what about if we do this, plus 2k pi, where k is some integer? What's going to happen here? Well, so this is the same. Is this true? Can we just arbitrarily add any component of 2 pi to this and still get the same thing? And you already know the answer is yes. Why? Because this part of the equation of the polar form is really just the angle that it's at. And if you spin it all around by 2 pi, either way, you're going to come back. Let's see that this is still true. This would be cosine pi over 2 plus 2k pi plus I sine pi over 2 plus 2k pi. Well, we know that cosine is periodic with period 2 pi. It doesn't matter that it's period 2 pi, period 4 pi, period 8 pi. Any factor, any integer factor of 2 pi is going to be periodic. So this is the same as cosine pi over 2. Similarly, this is the same as I sine pi over 2. So this becomes the same. And in general, and this is where some interesting things can happen. In general, suppose we have z equal to r1 e to the I theta. Well, this is also going to be equal to r1 e to the I theta plus, oh, and you know what? I was bad in that last example. I didn't put brackets around this. The I has to go with the 2k pi. So my bad on that notation. I was sloppy. You would write it like this: I theta plus 2k pi. Okay, and once again, I'm really sorry. The last time when I wrote down, I wrote e to the I pi over 2 plus 2k pi. I don't think that I did this, and that's absolutely necessary to do that to make this right. Okay, so pardon on that. this has some interesting ideas. Suppose we have this. Suppose you have z cubed is equal to 1, or this is the same as z cubed minus 1 equals to 0. What are the roots to this solution? Or what do you have? Z is equal to 1 to the 1/3. Well, we already saw that I to the 1/2 was equal to 1 over the square root of 2 plus I over the square root of 2. So things are getting weird already. We're done for today, and you've probably got a lot of information to sift through. I had a great time because I really like this stuff. I'll be back.